from the time of ancient mathematicians all the way through the mathematicians of the 1500s, they only had the tools of pre-calculus to work with. Problems that took years to solve during that time period are solved within seconds with the use of calculus and either computers or graphing calculators. However, it is pre-calculus that is still required to be able to set up the equations that model real-life situations. Hi, my name is Tom Atwater, and today's lesson is examining models of motion, consumption, and net change. In many applications, the integral is viewed as net change over time. The classic example of this kind is distance traveled, a problem that we discussed back in Chapter 5. Let's work out an example of interpreting velocity of a function. The figure on the next slide from a grapher shows that the velocity ds dt is equal to v of t equals 5 cosine t centimeters per second of a particle moving along a horizontal axis for 0 is less than or equal to t is less than or equal to 2 pi. Describe the motion. So let's take a look. Here's the graph. Remember that what we're really looking at here is a particle that's moving along a horizontal axis. I will start at 0, which is representative of here, and the graph above here, that is the graph from the grapher, remember, is not a position graph. It's a velocity graph. The position graph I'm going to show you down here. So here's what happens. It initially starts with a velocity up here of 5 centimeters per second. And it's to the right because it's positive. So this thing is starting this way at 5 centimeters per second. Now what happens is it begins to slow down until it actually stops right here at pi over 2. Then what happens is it starts to go to the left. To the left, that's what this negative velocity tells us. It starts to go to the left in terms of its position. And what happens is when it gets exactly to pi, it stops again, right? And then it slowly picks up again. It's still negative, though, until, I'm sorry, it doesn't stop there. It actually reaches a top speed of 5 centimeters per second to the left. Then it starts to slow down until what happens is right at 3 pi over 2, it stops again, right? It's 0 here. And then it picks up again and starts to speed back up to the right until it reaches a top speed right here at 2 pi of 5 centimeters per second to the right-hand side. Okay, so that's how you can translate a velocity curve into a position. Now, let's use the same problem to find the position for displacement. In other words, find the particle's displacement for the given time interval of if s of 0, in other words, the starting position is 3. What is the particle's final position? Well, of course, we have to remember that displacement, d, is equal to the integral of the velocity. So in this particular case, we are going to have the integral from 0 to 2 pi, because that's the interval we're looking at, of 5 cosine t dt. And when we integrate that, of course, we get 5 sine of t evaluated from 0 to 2 pi. And that will give us 5 sine 2 pi minus 5 sine of 0. And remember, the sine of 0 is 0. The sine of 2 pi is 0. So the displacement is actually 0 over that interval. Since it started at 3, 3 plus 0 is 3. So it actually finishes where it started. All right. Well, now let's calculate the actual total distance it traveled. Just because it went to the right, and then came back to the left further and came back to the right and ended where it was, there is a total distance traveled, which, remember, we take and integrate the absolute value of the velocity to find the actual the absolute value of the displacement to find the actual total distance it traveled. So let's move to that. Find the total distance traveled by the particle. So remember, total distance is equal to the integral of the absolute value of velocity. And we're interested in from 0 to 2 pi, which you have to remember that we found two different places where the velocity was actually equal to 0, meaning that it changed from positive to negative. The first one was at pi over 2, where it came down. At pi over 2, it had a velocity of 0. It stopped, and then it started to go to the left. And then at 3 pi over 2, it stopped again and started to come back to the right. So that what we're going to do is divide this integral up into pieces. And remember that what we're integrating is the velocity, which of course is the 5 cosine t. So what this would be is the integral from 0 to pi over 2 of 5 cosine t dt plus the integral from, it's the absolute value of 5 cosine t dt. Then we have from pi over 2 to 3 pi over 2 of the absolute value 5 cosine t dt plus the final section, which would be from 3 pi over 2 to 2 pi of the absolute value of 5 cosine t dt. Okay, so now what we have to do is anti-differentiate each one of those integrals, and we'll come up with 3 pieces that we then add together to get our total distance. So let's looking at this one. Of course, the integral of 5 cosine t is 5 sine t. So we have 5 sine t, and that's going to be evaluated from 0 to pi over 2. Then we have plus 5 sine t evaluated from pi over 2 actually to 3 pi over 2 plus we have 5 sine t evaluated from 3 pi over 2 to 2 pi. I want to show you how to deal with the absolute value now, because you need to put the absolute value bars around the entire evaluation of the integral. So that what happens is when you evaluate the integral and you end up with a negative number, we then take the absolute value of it. So I'm putting my absolute value bars around the entire term for each one of these. So now, what we know is this. Sine of 0, of course, is 0. So we know that's going to drop out. What we're interested in is the sine of pi over 2. The sine of pi over 2 is 1. 1 times 5 is 5. So for this section, we have 5. For the middle section, the sine of 3 pi over 2 is actually equal to negative 1. So that we have 5 times negative 1 for negative 5. Then we have to subtract the sine of 5 sine pi over 2. The sine of pi over 2 is positive 1. We multiply by 5, it's 5, but then we're subtracting it. So we have negative 5 minus 5, which of course is negative 10. But then inside the absolute value, we apply the absolute value, we get 10 as a positive number. So we're going to add that. And then in the last case, we have the sine of 2 pi is, of course, 0. Then we subtract from that 5 times the sine of 3 pi over 2, which we know sine of 3 pi over 2 is 1, times 5 is 5. even though we're subtracting it, it'd be -5, but now we apply the absolute value bars, and we get +5. So our overall answer for the total distance this traveled is equal to 20. All right, and that would be 20 centimeters based on the original velocity of 5 centimeters per second. So in summary, integrating velocity gives displacement. That is, it gives us the net between where it started and where it ended. But integrating the absolute value of velocity gives the total distance traveled. All right, great. Let's look at a strategy for modeling integrals. And the strategy is this. Approximate what you want to find as a Riemann sum of values of a continuous function multiplied by interval lengths. If f of x is a function, if f of x is the function and a, b is the interval, and you partition the interval into subintervals of length delta x, then the approximating sums will have the form summation of f of c sub k times delta x, with c sub k being a point in the kth subinterval. Step 2, write a definite integral, in this case the integral from a to b of f of x dx, to express the limit of these sums as the norms of the partitions go to 0. And step 3, evaluate the integral numerically or with an antiderivative. Let's take the U.S. oil consumption. The rate of consumption of oil in the United States during the 1980s in billions of barrels per year is modeled by the function c equals 27.08 times e raised to the t over 25, where t is the number of years after January 1st, 1980. Find the total consumption of oil in the United States from January 1st, 1980 to January 1st, 1990. So what we need to do here is integrate that particular formula over the interval from 0 to 10. So what that would look like is the integral from 0 to 10 of 27.08 times e raised to the t over 25 dt. If we plug this into our calculator using the n-int, which remember on the TI-84 plus additions comes up as fn and int. But if we plug that in, let me show you on the calculator what that window would look like. So let's switch, and here we have. So it's fint, the formula 27.08 e raised to the x over 25, and then the variable is x. The interval is from 0 to 10, and here's your answer, which is 332.96 billions of barrels of oil that were used during that time period. Okay, let's take a look at another way we can use this, which is to look at work and force. We're going to look at what's called the constant force formula for work is W equals Fd, where F is the force acting on the object for a distance of d. The unit of measure is either Newton meter or foot-pound. And Hooke's law, which is F equals K times X, yields the force, F, needed to stretch or compress a spring X units from its natural length. And K is the force constant. Let's work an example where we use Hooke's law. It takes 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring 4 meters from its natural length? So what we do is we know we're going to use F equals KD. And what we're told is that it takes 10 newtons to stretch it a distance of 2 meters. And that means K is equal to 5. And what that tells me is my equation is F equals 5 times D. So when it asks how much work is done in stretching the spring 4 meters from its natural length, we can plug in 4 for D to find the force, remember, because first we have to find the force. So the force is 5 times 4, which is equal to 20. Now, in terms of finding the amount of work done, what we have to do is integrate from 0 to 4 the force function, which I will change and replace the d with x. So what I'm integrating is 5x dx from 0 all the way up to 4. So what that gives me then is 5x squared over 2 evaluated from from 0 to 4. And when I evaluate that integral, remember when I stick in 0, it's going to be 0, so we're only interested in the 4. And 4 squared is 16 times 5 is 80 divided by 2 gives me 40, and it would be 40 Newton meters, because our original problem was in newtons and meters. Okay, well now it's time for you to try a problem. So here's the problem I would like you to do. It's a Hooke's law problem. A certain spring requires a force of 6 newtons to stretch it 3 centimeters beyond its natural length. What force would be required to stretch the spring 9 centimeters beyond its natural length? And what would be the work done in stretching that spring 9 centimeters beyond its natural length? We'll pause the video while you work on this problem, and when you are finished, restart the video to check your solution. All right, let's find out how you did on this problem. Let me go to a clean screen. And again, you start off with the formula F equals KD. And in this particular case, we know the force was 6 and the distance was 3, so K equals 2. Then we know that the distance was 9, so we have F equals 2D. F equals 2 times 9, which gives me a force of 18 newtons. Now we want to find the work done, which is the integral of the force, which I will replace my d with an x, so it's 2x dx, and it's over the interval of 0 to 9. All right, so let's integrate this, and we get x squared evaluated from 0 to 9. And of course, when we plug that in, we will get 81, and this will be Newton centimeters. So that's the answer that you should have gotten on your problem that you just did. Great session again today. So in this lesson, we looked at linear motion, we looked at consumption over time, a general strategy for modeling integrals. So be sure to work the exercises that your teacher assigns, and we'll see you next time.